Welcome to another intermediate algebra video. In this video, we'll be looking mostly at the product and quotient rule and then also at the midpoint and distance formula. So our objectives for this section are to use the product and quotient rules on radicals, to simplify radicals, which we've done a little bit of, but we'll kind of continue doing that in this section, and then use the distance and midpoint formula. Here are our notes for this section. The product rule. As we saw last time in the previous video, it's possible for this index number, on first looking at the product rule, to be something other than the standard square root. And so the n being there just signifies that it can be anything as long as these two are the same. So product is with multiplication. If we have the same index of a radical multiplying by another same index radical, you can multiply the inside pieces together. The same would be true if there was something on the outside as well. You'd multiply the outside stuff by outside stuff and inside stuff by inside stuff. Sometimes it'll be more helpful for us to pull things together in this way in multiplication, and sometimes it'll help to break them apart. So just keep that in mind. And then the quotient rule, quotient meaning division, is pretty similar. If you have the nth root of a fraction, you can break it apart to have the nth root of the numerator over the nth root of the denominator. And the n just shows that those numbers will be the same in any case. They'll all be square roots or they'll all be cube roots. And just like with the product rule, sometimes it'll be more helpful to start with the single fraction, and sometimes it'll help they're both a single fraction. Sometimes it'll help to have it underneath the radical, and sometimes it'll help to have it separate. So just know that using the product and quotient rule, you can go back and forth between these two. And then also we have the distance and midpoint formula. So distance formula is the square root of x2 minus x1 plus quantity squared plus y2 minus y1 quantity squared. And to use this formula, it requires an x1, y1 and an x2, y2. So they're just ordered pairs, just numbers that you plug in. The reason we see this formula in this section is that it's an application of a square root. And then the midpoint formula just goes hand in hand with distance. It's, remember on our graph, if we had 2 points, these are two different pieces of information. We're looking at either the distance between the 2 points, the length of the piece between the two, or the midpoint, the place that would be in the middle of the two. And the midpoint formula is to add the x's together and divide by 2, and the y's together and divide by 2 to get your x coordinate of the midpoint and your y coordinate of the midpoint. And you should present the midpoint as an ordered pair because it is an ordered pair. You're talking about a specific location on the graph. All right, so let's take a look at using product and quotient rule in order to simplify. So the directions will say simplify, and all variables represent non-negatives. So just needs to be said for us to be able to do these problems. So the first thing we have is the square root of 6 times the square root of 7. And we can use the product rule on this. Since they are the same type of radical, they're both a square root, we can multiply them together underneath that one root. So underneath will be 6 times 7, which is 42. Now, the simplifying part, simplify can mean so many different things. For radicals in the end, it means making sure you don't have any pairs underneath the radical. So we can take 42 and break it down. We'll go right back to the 6 and 7 that we started with. And then 6 breaks down to 2 and 3. The 7 doesn't break down anymore. And the only way we'd be able to simplify this any further is if we had a pair somewhere in this list, a repeat. And we'd be looking for a pair because it's a square root. We don't see any pairs there, so square root of 42 is as good as it gets. The next one, the square root of 5 times the square root of 19. Again, these are like radicals because they have the same index. They're both a square root. So we can multiply those together, inside by inside. Now you might be wondering, well, can I actually multiply them since 5 and 19x are not alike? You're right, they're not like terms, but with multiplication that doesn't matter. You can multiply anything together. So 5 times 19 gives us 95, and then no x times an x leaves us with an x. Again, the only thing left to do would be to make sure that you couldn't take any pairs out of there. So looking back, the 95 came from 5 and 19, and neither of those break down any further, so there's no pair that can come out from the number. And then from our variable, we only have one single x, and the only way we can take any out of a square root is if we have at least 2. So this is as simple as this one gets. All right, the next one. We have the square root of 5 over 49. In the previous video, we saw some where we had a perfect square on top and bottom. This is not the case here, so the quotient rule would be helpful for this problem, and that we can first separate to have the square root of 5 over the square root of 49. And then we can move forward hoping to simplify each one individually. So in our numerator, square root of 5, nothing we can do. And in the denominator, square root of 49, well, that's one of our perfect squares, and that's a 7. Remember, 49 is 7 times 7. There's a pair of 7s, so 7 comes out. So we get square root of 5 over 7. And there's no more simplifying that can be done here. We don't have any numbers top and bottom that can simplify or cancel out. And that radical was already looked at to be simplified, so there's nothing else we can do on that one. All right, let's look at square root of 50. For this one, the only thing we can potentially do is look for pairs inside. So there's a couple different ways you can do this. One way is to take 50 and break it down. 2 times 25, and 25 is 5 times 5. So you could first take this and write it as 2 times 5 times 5. And then look for pairs, just like we've done before. So we have a pair of 5s, which means a 5 comes out. And now we haven't seen this yet, but something is left over and it stays inside. If it doesn't have a pair to come out with, then it's stuck inside. So we could simplify this one to say 5 square root of 2. Another option, and this kind of uses the product rule more specifically, is to look at 50, take everything inside, and look for perfect squares inside the number. So in 50, we can see that the breakdown could be 2 times 25, and hey, 25 is a perfect square. So let's say this is an alternate way. Alternate method. So instead of fully breaking down to primes, we could more specifically look for perfect squares. So we could write this as 2 times 25. And that doesn't change anything. This still represents the same thing. Then we can use the product rule to separate these into 2 individual square roots. Once they're separated like this, you can clearly see, well, the square root of 25 is a perfect square. That is 5. And then the only thing left, and maybe you wrote it a different way to begin with, would be to reorder these. So typically, if there's a whole number, so a 5, something that came out, we write it in front of the radical. It's just a standard practice. It's not necessarily wrong, but you aren't going to see it written like that anywhere else. It'll always say the piece that came out, 5 square root of 2, with the radical after it. Now, there's no preferred method of these two. You can absolutely choose one or the other. And in fact, if I were doing these on my own, I would definitely alternate between the two methods, depending on the numbers. If I looked at 50 and I recognized quickly that, hey, there's a 25, that's a perfect square in there, that's probably the route I'd go. But if I look at it and that's not something that jumps out at me, well, then I'm going to go down to primes. Or start breaking down until I see a perfect square. But just know that both are possible. All right, let's keep going. So let's simplify some more. All variables, again, are non-negatives. Now we have variables involved. So we have 2 square root of 20. Looks a little different because there's a number already on the outside. The only difference for this type of problem is that it's sort of like some of the work has already been done. So someone already broke some stuff down inside, already found a pair of 2's and brought it out. So it just stays outside. It's part of the answer. It'll interact with anything that comes out of the radical. All right, so we can take 20, and I'll do both methods for this one. We can take it and break it down to 10 times 2, and then 10 to 2 times 5. So inside I have 2, 2, and 5. There's a pair of 2's, so a 2 will come out. Now there's already a 2 on the outside, and another 2 came out. So what we have on the outside is 2 times 2, and then 5 inside. And that ultimately simplifies to 4. 4 square root of 5. The expectation on pretty much any radical problem is that at the end you make sure there's no perfect squares inside. Okay, so the alternate method for this one, starting with 2 root 20, would have you look at 20 and see if there were any perfect squares inside that number. So you can go through the list of perfect squares. Now the first one in the list really is 1, but it's not very helpful. The next perfect square from 2 squared would be 4. The next one would be 9 for 3 squared. Then 4 squared is 16, 5 squared 25, 6 squared 36, all the way continuing on. So you're looking for one of these numbers to be able to divide out of what's inside. So 1 isn't going to help us. Can we divide 4 out of 20? In fact, we can. When we broke down 20, we didn't start with 4, but we could have. So it's just showing you that either method absolutely works. If we took 20 and started with 4 and 5, then we see the perfect square. So instead of writing 20, we could write 4 times 5 underneath. Then use the product rule to break these into 2 separate radicals. So we have 2 on the outside, and then there's a square root of 4 and a square root of 5, and they're all being multiplied. Well, this square root of 4 turns into a 2, because it's a perfect square. 2 times square root of 5. The 2's multiply, and we get the same answer that we got doing it the other way. 4 square root of 5. So pick one, alternate, it's up to you. All right, the next one. Now we have variables involved. So remember, you deal with variables in one way and the numbers in another. So we have square root of 36, square root of 36 x to the 5th. Now if you want to, you could separate using the product rule. You could separate the 2, and you could separate in lots of different ways. But for some people, this is preferable. I'm not sure I would suggest this way if there are variables involved, but it's up to you. So we have square root of 36. Oh, not squared. There we go, to the 5th. The square root of 36, which is a perfect square, 6. And then the square root of x to the 5th. Remember, with x to the 5th, we have 1, 2, 3, 4, 5 x's. We're looking for pairs. There are 2 pairs, so 2 x's come out, and then there's a single x left inside. One way to get to this answer. Now, you definitely don't need to make the separation. You can absolutely go from this initial problem to 6. Well, there are 5 x's, there are 2 pairs, so 2 come out, and then a single x left inside. It's your call. You don't have to separate like this, but the product rule allows you to do that if you wanted to. Either way, you will come up with the same simplified answer. All right. Let's do a little bit more practice. Again, simplify, all variables are non-negatives. So our next problem is the square root of 32 x to the 8th y to the 9th. Deal with the numbers and then deal with the variables. So the 32, you can choose whichever way, look for perfect squares, or go down to primes. I'm going to go down to primes for the time being. Start with 2 and 16. 16 is 4 and 4. Each 4 is 2 and 2. So underneath we have 1, 2, 3, 4, 5 2's. And then x to the 8th, y to the 9th. So we're looking for pairs. We have a pair of 2's and another pair of 2's. So a 2 and a 2 come out. And I'm going to leave some space so I can deal with the numbers and be done with them. And a 2 is left inside. Then look at the variables. You can list them all out. You can use your fingers. You can just think through it. There are 8 x's. We want pairs. 1, 2, 3, 4. And they're all used. So 4 x's come out of the radical. And we have 9 y's. In a similar way, you can look at all of them, pair them up. We have 4 pairs and a single y left inside. So 4 come out and a single y is left inside. And then just pull it all back together. So the only other thing you can do to clean this up is actually multiply the 2 times 2, which gives you 4x to the 4th, y to the 4th, square root of 2y. Maybe when you started to break down the 32, you noticed that this 16 is a perfect square. And so you could right away say, hey, there's a 2 that's going to be left inside. It can't do anything. But this 16 is a perfect square that'll come out as a 4. So whichever way you want to go through the problem, it's up to you. Okay, the next one. We have a negative square root of 252 x to the 8th y to the 19th. 252. It's the same process with a large or small number. You can look for perfect squares or you can look for pairs. So I'm going to break down 252. It's definitely divisible by 2, and if we divide by 2, we get 126. This 2 can't go any further. The 126 can break down to 2 and 63. 2 can't go any further. Then the 63, a lot of different things could jump out at you. 9 times 7 jumps out at me. 7 can't go any further. And this 9 goes down to 3 times 3. So, to be clear, we have 2 times 2 times 3 times 3 times 7 times x to the 8th, y to the 19th. And we're looking for pairs. We have a pair of 2's. So a 2 comes out. We have a pair of 3's. So a 3 comes out. And then this 7 doesn't have a pair, so it's stuck inside. And don't forget this negative. It just keeps coming down and is part of the answer. Remember, the negative on the outside is not a problem. It's only on the inside where you have to make the judgment call. Okay, then from the variables, we have 8 x's. We want pairs. 8 of them. There are 4 pairs. X to the 4th. And I'll draw it out for this one. Remember, you can still draw out all 8 of them and look for 1, 2, 3, 4 pairs. Just look for all the pairs. And then the y to the 19th. Imagine 19 of them. A string of them, how many pairs would there be? We'll have 9 pairs with 1 left over. And the only thing we can do to clean this up is actually multiply 2 times 3, the items that came out. X to the 4th, y to the 9th, square root of 7y. If you're looking for more of a foolproof way to simplify these, the foolproof way is definitely using the tree and going all the way down to the primes. If you were to look for perfect squares, let's say we looked at 252 and we said, is there any perfect square? Let's try a 4. if we divided a 4 out of that, we'd have 4 and 63. And then we might say, hey, there's a perfect square. Square root of 4, square root of 63. Simplify that, and then not do anything else with the 63. When in fact, the 63 also has a perfect square. So just be careful if you use that method to make sure you check the other piece that's left over, in this case the 63, to make sure that there's not another perfect square hidden in there. If you miss one of them, then the answer is going to be marked as wrong. It needs to be simplified as far as you can go. All right. I think one more example. Yeah. Let's look at distance and midpoint before we do some practice problems. So here's the question. Find the distance and midpoint of the 2 points given. Distance and midpoint. These are two totally different questions. I'm going to start with midpoint, since that formula is a little more basic. I'll write the formula again. It's x1 plus x2 divided by 2, and y1 plus y2 divided by 2, giving you an x-coordinate and a y-coordinate. So our ordered pair, 5, 2, and negative 1, 4, you can label them however you want to, x1, y1, x2, y2, and then just plug them in. So our x's are 5 plus negative 1 divided by 2, and our y's, 2 plus 4 divided by 2. In the numerator, we get 4 for the first fraction, and the second one we get 6. And these each clean up to 2 and, whoops, that's 2 and 3. So the midpoint, the place located directly in the middle of these 2 points, is 2, 3. And the application of it here might not seem relevant. It's just midpoint and distance formula often go hand in hand. The distance formula will feel a little more in the same wheelhouse. So the distance formula, let me remind you, x2 minus x1 quantity squared plus y2 minus y1 quantity squared, all underneath a square root. So it's the same ordered pair, x1, y1, x2, y2. And it's possible in future classes where you'd be given problems, maybe you knew something about x and you knew the distance and you'd solve for a different piece. In this class, all you're going to look at is actually finding the distance given 2 points. So there won't be any other manipulated version of this question. It'll just be different numbers. All right, so let's plug in what we have. Our x2 is negative 1 minus x1 is 5 quantity squared, plus our y2 is 4 minus y1 is 2. And then it's a matter of simplifying and simplifying. That's it. Underneath, inside each parentheses, we can combine. Negative 1 minus 5 is negative 6. 4 minus 2 is 2. Then square each one. You might be wondering, hey, a square root and a square undo each other. Can I cancel them out? You can if it's all squared and it's all multiplication. The problem arises when there's an addition here. And you'll see why when we go through the problem. So you might be wondering, is it just negative 6 plus 2? So if we square this, we get 36. Square this, we get 4. So our distance is the square root of 40. But in order for us to simplify this fully, we need to look for any hidden perfect squares or pairs inside 40. So if we break down 40, 4 times 10, 2 times 5, 2 times 2. We have a pair of 2's and a 2 and a 5 left inside. So the 2 comes out. What's left inside is 2 times 5, which is 10. And there is our distance. So in the end, this did not end up being canceling out these square roots. It didn't end up being negative 6 plus 2 or even 6 plus 2. It's 2 square root of 10. So just know that the square undoing a square root or vice versa only applies when it's all multiplication. The addition in there causes that not to work. All right, so distance and midpoint between these two ordered pairs. And you don't ever have to for this section. You don't ever have to graph them, but just so you can get a feel for what this means. We have a point here and -1, 4. So the distance between the two is 2 root 10. And then the midpoint right in between is 2, 3. And it may not give you a nice point like this every time. And based on my drawing, you can see it doesn't quite look perfect, but on a printed graph, it would look accurate. Okay, so let's do some practice, some simplifying where all variables are non-negative, and then also find the distance and midpoint between the 2 points. Go ahead and pause the video, and we will go through them together in just a moment. All right, so the first problem, simplify. We have square root of 50 times square root of 2. We can multiply those together using the product rule to get the square root of 100, and then simplify. This is a perfect square, which is 10. Hooray! An alternate way of doing this problem would be to simplify and then multiply. So if you first took the 50 and broke this down to 2 and 25 and then 5 and 5, you have a pair of 5, so a 5 can come out with 2 on the inside, multiplying by square root of 2. Then actually multiply these together. You'd have 5 on the outside and the square root of 4, which would turn into 5 times 2, which is 10. So whichever way you went through this problem would be fine. All right, the second one, some of the work has already been done for us, the 3 on the outside. So let's see if there's anything in 54. This can break down to 2 and 27, 27, 9 times 3, and then 9, 3 times 3. So the only perfect square is a 3. There's already a 3 on the outside, then another 3 comes out from the pair. Let's leave some space for the variable. The numbers that are left inside are a 2 and a 3, which is 6. And then we have 6 x's, so we're looking for pairs, 1, 2, 3 pairs. They're all used. Nothing goes inside. Clean this up. We get 9x cubed square root of 6. All right. Then distance and midpoint between the two ordered pairs, 3, -2, and 1, 8. We'll start with midpoint. This would be x1 plus x2 divided by 2, and y1 plus y2 divided by 2. We get 4 over 2 and 6 over 2. And hey, same ordered pair as the last one. So here's our midpoint, and as I mentioned, it should be written as an ordered pair because that's what it is. And then distance, square root of x2, which is 1, minus x1, which is 3, quantity squared, plus y2, which is 8, minus y1, which is -2, quantity squared. And it's just a matter of cleaning things up and evaluating whenever possible. So in each parentheses, 1 minus 3 is -2. 8 minus -2 is positive 10. Remember, minus negative turns to plus. Square each one, we get 4 plus 100. Add those together, 104. And then look for any pairs in there. 104, we can divide out a 2. 52 from the 52. 2 and 26. From the 26, 2 and 13. So we definitely have a pair of 2's. So a 2 comes out, and what's left inside is the 2 times 13, or 26. So the midpoint is 2, 3, and the distance between the 2 points, 2 square root of 26. Okay. All right, so in this video, we looked at multiplying using the product rule, dividing using the quotient rule, and overall just simplifying. And then we also looked at the application of the distance and midpoint formula. If you have any questions, feel free to email me. Otherwise, I'll see you soon for another video.